So first, just a brief mention of ensemble methods in general. So what's coming up for the rest of today are all different instances of ensemble methods. An ensemble method is where somehow or another we're combining prediction functions derived from different models. There's two main types of ensemble methods. There's the parallel and the sequential. The parallel ensemble methods is you could imagine starting a whole bunch of computers all training different models on your data, and then you combine them in some way. Sequential ensemble is where you fit a model, you kind of look at your results, and you see how it does, and you maybe adjust some things, and then you fit another model on some modified data set, or in some way, it's not the same problem exactly. And then maybe you do another one. And I think intuitively the best way to think about it is in each step, you are correcting the errors from the previous step, or from the previous steps. And at the end, you could imagine the simplest case, what you're doing is kind of adding together the models, the prediction functions that you got at each step, where you think that each step was trained to fix the errors of the previous step. That would be kind of a very straightforward version of sequential ensemble methods. And that specific thing I described, we'll talk about in a bit. All right, so ensemble methods. So we're going to talk about parallel first, and in particular, we're going to talk about bagging. And bagging is basically about, in a regression setting, for instance, averaging the predictions of a bunch of models. Okay. So let's just quickly remind ourselves why averaging might be a good idea at all. And we've kind of spoken about this back when we talked about L1 regularization, where I was arguing that sparsity is not always that great, because just because 3 variables are highly correlated doesn't mean you only want to select one of them. If you average them together, you could potentially, or use them in combination, you could potentially do better by reducing the variance. Maybe you recall that argument. Well, we're going to make the same argument here again as a review. So imagine you have n random variables, z1 through zn, and they are all identically distributed with mean mu and variance sigma squared. And your goal is to estimate the mean mu, right? So one lousy way to do it is to just take z1, right? So z1, what's the expected value of z1? Mu. So z1 is an unbiased estimator of mu. Is it a good estimator of mu? What's its standard deviation? Sigma, yeah. OK. So not a great estimator. Why? What could we do that would be better than just using z1?
Use all of them.
You could use, what would your statistic be on the full data set if you want to use them all?
Take the average row from z1 to zn.
Sure. Take the mean of the z's, z1 through zn, and that could be your estimator of a mu. Great. What's the standard deviation of that estimator? Sigma divided by square root of n, exactly. That is the standard error of your estimator, right? And you could work that out from basic properties of variance. OK. All right. If you want to look later, this is the kind of worked out version of why the. Well, I didn't really work it out. I just wrote it down. OK. So the average is clearly preferred over a single example. Why? So what has happened here is that the expected value of the mean is still mu, but the variance has gone from sigma squared to sigma squared over n when we took an average. So the variance has shrunk, error is smaller. That sounds like a win. And the question is, can we use the same idea for general prediction functions, like mapping from x to y? Here we're just estimating a single parameter. So that's where bagging comes in. So we're going to kind of get at this the same way we got to the bootstrap, which was first we're going to imagine we have B-independent training sets, right? Same distribution. And we have a learning algorithm that we run on each of those training sets, and we get B prediction functions. And the idea would be, what if we took the average of these B prediction functions learned on B-independent training sets? The expected value should be the same. expected value of the average will be the same as the expected value prediction of any one of these individual things, but the variance will reduce if we've assumed that training sets are independent, in the exact same way as when we average a bunch of z's together. So let's see if I've written that down. Yeah. Great. So the variance of the average is 1b the variance of the original prediction. So 1 over square root of b for the standard deviation. So if we could have these independent training sets, the best thing to do would be to build your model on each, then average the predictions, and you'd have the same expected value and smaller variance. This is good. This is a win. All right, so the question is, of course, what can we do? We don't actually have independent training sets. Can we use bootstrap samples and have the same type of win? So we don't really have B independent samples, but we have B bootstrap samples, and we train a model on each of those, and then we average. Will we get the same type of reduction in variance? That's what bagging is. Bagging, we do B bootstrap samples from our original sample. We train B decision functions. We combine them in some way. So now we've generalized a bit. We don't necessarily have to average. Averaging makes sense for regression, but what about for classification? OK, you're going to need a different combination function. How do you combine? So for binary class predictions, you could do voting, like majority votes. If you wanted to do soft classifications, if you had soft classifications, you could average the probability distributions. There are different kind of straightforward ways to combine prediction functions. And this is the idea of bagging. So what's going to keep us from, what will keep this from being a big win? Well, the fact that it's not really independent samples. So the fact that these are bootstrap samples and not truly independent samples is what's going to, keep us from achieving the full reduction in variance that we might hope for. All right, this is again Leo Breiman proposal. So this just summarizes what we're saying is that this bagging prediction function, which averages over in this case averages, or in general combines the prediction functions from each of the bootstrap samples, we hope it should have the same expectation and smaller variance. That's the hope. That's the hope. OK. So I don't have any theory on this. I don't have a theorem for you. Not for lack of searching in the literature. It's hard to find convincing theory on bagging. A lot of it is hand-waving in the same way I've waved in front of you with like the notion of inspired by independent samples and variance reduction and that sort of thing. There's a little bit more than that, but I haven't found it. It may exist. I haven't found great theory for this. But as a technique, it has some other nice benefits. There's this cool thing, which is out-of-bag error estimation. So we're going to do bagging. So we're going to do these B independent bootstrap samples. We're going to train a model on each of them. And one thing you'll remember about the bootstrap sample is that a non-trivial amount of points in your original sample do not show up in your bootstrap sample. Something like almost 40%, right? So 37%, the expected number of examples that do not show up in any given bootstrap sample. So what's cool is that for that particular model built in that bootstrap sample, you can consider those 37% of things that don't show up as things you can validate your model on. They're out of sample for this particular model. Right? When we get to the second bootstrap sample, it's going to be a different roughly 37% of examples that don't show up in the training set for this model. And here, a different set of roughly 37% of examples not in this training set. See what's going on here? Yeah?
Sounds like cross-validation.
It's reminiscent of cross-validation. It's reminiscent of cross-validation. So, all right. So now for any particular example in your original sample, it's going to show up in roughly 63% of the bootstrap samples. Maybe it shows up in this one, missing from this one, shows up in this one, and this one, but not this one, for example. So we have our B models from each of the bootstrap examples. We combine them, all right? But what we can do, if we want to kind of do something cross-validation-ish, is what we could do is for each point, x1, we could find all of the bootstrap samples that don't include x1 and combine the models from just those bootstrap examples. And then see how it does on x1. So that would be the out-of-bag performance estimate for x1. Because x1, out-of-bag is to say that x1 did not show up in the bag of training examples used to build the ensemble you're using. So you can use these out-of-bag observations. And every example will be out-of-bag for some subset of bootstrap samples. And you can kind of evaluate the performance of the out-of-bag performance on each training example by combining all of the bootstrap models that were not trained on that particular example. Okay. So this gives you a clever way to assess performance out of sample without using an extra validation set or doing cross-validation or anything. It's just kind of natural from this bootstrap approach, the bagging approach.
You talked about assessing performance in this context. Could we also imagine almost like fitting coefficients on each of those for that xi?
Oh, so it sounds like you're saying rather than combining by a straight average or some voting or something straightforward, could one do something a little fancier, like weigh them based on maybe performance on the out-of-bag examples? Sounds interesting, sounds promising. I haven't heard of that being done, but I don't see any reason why you shouldn't give it a try. Sounds, yeah.
It's not guaranteed to be greater than 0, is it?
No, there's no guarantees any of these things are greater than 0, right? Yeah. All right. Okay. All right. Any questions on kind of the idea of bagging, how it connects to Bootstrap? So, yeah.
Just to make sure, so we don't need to split the data set in this case for testing separately, correct? Is the assumption correct?
Yeah, so this is kind of analogous to doing cross-validation or having a validation set. Yeah. Yeah.
Do you know the distribution of the percentage of out-of-bag samples? So the mean is 37%, and what is the variance of this distribution?
I don't know. I have to think about that. I think we should be able to figure that out, but I don't want to think about it right now. Let's come back to it.
So I just wonder how wide it is and how narrow. So what is the?
Yeah, I don't know. I think we could figure it out, but I don't know off the top of my head. Yeah. Good. Okay. All right, so just a quick illustration. 5-dimensional input space. It's a classification problem. We're going to build trees. And so this was the tree on the original sample. And then we did 5 bootstrap samples, 2, 3, 4, 5. Each tree looks quite different, right? It's built on different data. And you can combine these classifications in various ways. You could do majority vote. You could do average and hope that gives you some kind of estimate of a probability. Different things you could do. So here's kind of a plot of how things do with 2 different ways of combining. So here we have, on the x-axis, the number of bootstrap samples. So how many of these bootstrap models are we combining? And then 2 different ways to combine. One being consensus, which is the yellow one. So that's like voting. And the other, in the green, is averaging the predictions to get a probability. And they seem roughly the same. Consensus is a little bumpier. And you could also see that things, in this case, things level off pretty quickly. So in this example, you didn't need too many bootstrap samples to kind of get your gain, but you certainly had a gain from the original tree. So the performance of the original tree is quite a bit worse than bagging with maybe 10 or so trees. Okay.
What is Bayes mean?
Sorry, again?
The bottom says Bayes. What is that?
Oh, what's the Bayes? Good question. Well, anytime we have a performance for Bayes means this must have been simulated data, because Bayes prediction function, remember, is the optimal, the best possible prediction function. So 20% error rate from the Bayes prediction function means that there's some noise in the class label that's not predictable. Yeah. Great. Yeah. So bias and variance. Bias and variance have a very precise definition when we're talking about decomposing square laws. I mean, bias and variance for a particular point estimator is, we already defined, that's straightforward. But people also use bias and variance when they're talking about prediction functions. And there's a nice decomposition when you talk about square loss, and we can get into that some other time. But when people talk about bias and variance, in casual usage, they often mean something not quite so well defined, but I'm going to try to give you a flavor of what they have in mind. So when you, for instance, take a hypothesis space and you restrict it, you would call that biasing. You're biasing your estimate towards the restriction of the model that you created. A bias is, you could think about it, a bias as being pulling your prediction function away from the prediction function that that minimizes the empirical loss, the loss in the training error. And you could think of it pulling it away from the best and towards something that's usually simpler. Like when we did the L2 regularization. L2 regularization you could think of as a bias. You're saying, I want my coefficients to be closer to 0 than they would be if I weren't doing this regularization. So that's bias. And a variance, so decision trees that go very deep would generally not be very biased because you can fit everything very well. And then pruning decision trees so that they're smaller, that would induce a bias in the sense that you're not fitting the data as well, and you're asking that your function be smaller, your tree be smaller, simpler. Variance, the way people usually use variance, what they often mean is something that is probably better described by the word stability, and people use stability as well. And the notion here is that every time you get a new random training set, your prediction function will change, of course. But if it changes quite a lot, then we'd say it's a very unstable training procedure. And if it doesn't train much from sample to sample, then it's stable. And so a high variance model would be unstable. So every time you got a new training sample of the same size, the prediction function would be quite different. So trees are generally described as high variance, unstable. And that's kind of illustrated by the fact that the shape of these trees changes quite a bit on every sample. All right. Linear models are generally thought of as kind of high bias because they're restricted to linear functions. It's like a very specific model class. But low variance, which is anytime you resample, your linear prediction function doesn't change that much. These are just kind of stuff people say, right? Linear models, low bias, low variance, high bias. Tree models, low bias, high variance. Now, why are we talking about these things? Because there's some more stuff people say, which is, when does bagging work? And what people observe is that bagging works well when you are using models that are low bias, high variance, like trees. Why might that make sense? Because kind of idealized bootstrapping, where each of our samples was actually independent, there we can prove that the expected value stays the same. So if you're unbiased, you're still on point. But the variance goes down as you average things. So we have bootstrap samples. So we don't have the same theory. They're not independent. But the notion is the same, that by averaging these bootstrap samples, we could decrease the variance. So if you start with something that has high variance, we can maybe control the variance with bagging. If you had something that has low variance to begin with, like a linear model, bagging doesn't seem to help that much. Okay. That's why we usually see bagging with trees. Okay. So, but there's a little nugget in what I just said, which is that the thing that keeps us from great variance reduction is the fact that our bootstrap samples aren't really independent. Right? So if we have a large variance and the samples are independent, we can reduce that variance by averaging. So the issue might be that we don't have independence, enough independence when we do bootstrap. So what random forest is about is finding a way to try to get more independence between our models from each bootstrap, for each bootstrap sample. So the way they do that comes back to an idea Joy mentioned earlier, which is that you can insert some randomness into how we build our trees. Right? So by inserting more randomness, we're hoping to decorrelate, to make more independent the models built on each of these training sets. All right. So in a sentence, random forest is bagging decision trees, so bootstrap samples, build a tree on each, combine them, but we're going to modify the tree growing procedure in a way that hopefully makes things more independent. And what are we going to do? The key step is anytime we're trying to decide on a split for a node in the building of the tree, rather than finding the feature that's the best, we first randomly select a subset of features and only find the best in that limited subset. That's it. That's random forest. Random forest is that tweak on top of bagged decision trees. So, if you have 100 features and you're only searching from a random set of 10 at each node, and the 10 you select change for every single node. It's not like you select 10 for the whole tree. Every node you get a fresh selection of features to choose from. All right. So typical would be square root of the number of features. Extreme random trees or extremely random forests, I forget the name exactly. There's just one feature randomly chosen. And you can view m, the number of features that you're randomly choosing, as a hyperparameter to tune, if you like. Here's just a little illustration of performance of random forest as the number of trees grows, as the number of bootstrap samples grows, and then for 3 different sizes of features that you're choosing from. So m equals p, this yellow line, this is straight bagged trees, not random forest. Blue is random forest where you're selecting randomly half the features to choose from, so no improvement. But when you do square root of the number of features to choose from, some improvement. Right? It's just one example. It'll be different for every data set. The point is that varying m, the size of the number of features you're restricting to, can make a difference in performance. And again, the intuitive idea that people carry around for why this is helping is that we're creating more independence between our models. And so we hope that the remaining variance can be reduced more.
So it seems that the non-independence was from data not being independent, right? And not
The non-independence was because, so when we say independence, what we want is kind of an independent draw from the true distribution. But these bootstrap samples, they're independent draws from a single sample. And so kind of conditioned on this sample, they're independent. But they're all connected because they all have the exact same values from the initial draw. So that's the dependence that we're worried about.
right. And so I guess the reason the models are correlated is because the data input is somewhat correlated. But somehow making the feature sampling less correlated solves that problem? That seems a little...
No, well, so, OK, well, let's go on some steps. So you're skeptical that randomizing the features will make things less related, less dependent.
Since
Because the data is the same. Well, even if we had the same data set, not bootstrap samples, but the same data set every time, and we used random feature subsets, we would still get some. Let's lighten up our kind of technical understanding of dependence and just think about diversity of trees that we end up with. Different shapes corresponding to different prediction functions. So yeah, introducing the randomness in the features will create a larger diversity of tree shapes and stuff. Even if the data is exactly the same.
However, this randomness is sort of a subset of the features, right? So you're restricting, isn't that also introducing bias under this slide of like sort of restricting the model?
Yes, so that's a good point. So if you're restricting the model, aren't you introducing bias? Potentially, but I don't think that's such an issue with random forest, because in random forest, I didn't mention this yet, but in random forest you build very deep trees, so very low bias trees. So each individual tree in a random forest tends to overfit quite a bit, but after bagging them together, they have nice performance. All right, see if I have a note on that. No.
If you fit deep enough, though, doesn't that, eventually get to the point where if you go deep enough, eventually you've got one leaf node for every point, and then all your trees actually are identical despite the fact you built them through different methods?
Well, that's a good question. So if you build your forest all the way to the limit, every tree goes to the limit of every element being in its own partition. It's not clear that they're the same trees, though.
Not exactly the same trees, but your leaf nodes end up all being the same because there's one for every point.
Yeah. So the predictions in that case would be the same on the training examples, but they won't necessarily be the same on new examples, because the boundaries of the regions containing each individual point will be different. That's one thing. Another thing is, in practice, you make them very deep, but you don't necessarily go all the way to 1. You have some minimum leaf size, like 3 or 5 or something.
And the other question I had, so we now have two sources of randomness. One is the sampling down to M, and one is the sampling of the bootstrapping.
That's right, 2 sources of randomness, the bootstrap sample on the data, and then the feature subsample, that's right.
I guess what I'm wondering is, for small enough M, do you still need the bootstrap, or do you have enough randomness due to the...
Yeah, so the question is, for small enough M, do you need to bootstrap? That's a great question. I don't know. I don't know how that would work because that was kind of what I was suggesting. Like, what if we didn't even bootstrap? You'd still. I have no idea. I'd be very interested to see how that compares.
I guess can you give some examples on problems that are typically solved with
Can you say it again? Examples of what?
Of problems that we typically use things like random forest or like bagging.
So yeah, so random forest. Basically, it's good to know about bagging, because you can bag anything. It's just averaging stuff on bootstrap samples. But random forest is really the technique that people use. What do we like about random forest? It's highly parallelizable. Every tree can be built in parallel. There's really not a lot to tune in terms of hyperparameters. You kind of how deep you build the tree and how many trees. And now, do you think you could ever overfit with too many trees? Not so much. That's something to think about. So with bagging methods in general, you expect to always do better, maybe not much better, but always do better by having more bagged examples. So random forest is kind of great for those reasons. Also, we haven't gotten into them, but there's a lot of built-in. First of all, they're built on trees, so they handle missing data. That's nice. There's a lot of built-in methods, heuristic, but in any case, potentially useful, like for variable importance and stuff like that. I mean, random forest is a go-to method. It just, it's certainly much slower than linear methods, but maybe faster than a giant neural network. So, yeah.
Sounded like the scikit-learn implementation, in your opinion, is pretty immature.
For trees, it's a little bit weak, yeah.
Are there other libraries that are better, or?
In Python, I'm not super familiar with
In
the
R,
tree
definitely.
library. Yeah, in R, I think part of it is that the community that produced most of the tree-based methods, including trees, cart, and random forest, and gradient boosting, and by the way, lasso and elasticnet, are all statisticians who would first write in, well, Friedman writes in Fortran, but anyway, mostly in R, or their students would write in R or C++. And they were also developed before Python really became such a strong language for data science. So that's, I think, why you'll find most of that stuff. Things get transferred over to Python when they are kind of as needed.
Or something.
Yeah.
Instead of doing the pruning from the bottom up, how about if you just stop building your tree when you reach, say, n equal to something?
Yeah, that's what scikit-learn does. They stop building a tree when you get to a certain stopping condition, like not enough examples in the node or not enough reduction. Yeah, that would be standard.
Does it work well?
Yeah, it works well enough. I think also another reason sklearn doesn't get too elaborate with its tree-based methods is that using a plain tree, people do it, but if you want to get the best performance these days, you do not do it. If you want to get the best performance prediction-wise, you do some kind of ensemble of trees, either a random forest or gradient boosted regression trees, which we'll get to next time. And that's where you go for the best performance. And in that case, it's not clear that pruning is as important, basically.
Regarding the ensemble method, is it always that you have to take a similar models, like all trees you need to combine, or you can take different?
OK, so the ensemble methods, generically, you can combine models of different types. There's something called stacking, where you could build a bunch of models of different types, and then you build another model on top of those that fits how to combine those models. So you might have, for instance, a lasso or elasticnet linear model combining the predictions of 100 different fancy models that you came up with. I don't know if you guys remember the Netflix competition from, I don't know, 10 years ago already, where the winning teams were combining, I don't know if it was hundreds of models using some kind of stacking method. Yeah. That'd be yet another way of ensembling. Yeah.
I've heard a lot of Kaggle competition winners end up just being like these bizarre trees of XG boosts on top of each other with lots of different tuning parameters.
So you're saying that Kaggle winners have, are they kind of sequential ensembles of XG
They'll do
boosts?
like a stacking with like layers of different XG boosts with different tuning parameters, so they perform slightly differently. And I don't know the details. It's just sort of word on the street.
Yeah, that sounds about right. Different crazy ways to combine XG boost models, which are instances of gradient boosting that we would talk about next time.